The night sky holds secrets that have defied explanation for centuries. You are looking at a cosmic puzzle box filled with 26 unsolved mysteries buried in the stars. From a silent force pushing the universe apart to sudden screams of energy from distant galaxies, these enigmas challenge everything we think we know. By the end of this journey, you will see the cosmos in a completely new light. Why does the universe appear to have a strange alignment just for us? And what is the true nature of the invisible matter holding galaxies together? What single cosmic mystery makes you question your place in the universe the most? That discovery of an accelerating cosmos was a shock to the very foundations of physics. We expected the universe's expansion to be slowing down, pulled back by the collective gravity of all the matter within it. Instead, we found it was speeding up, as if some invisible repulsion was stretching the fabric of space itself. This mysterious force earned the name dark energy, and it is not a small component. Dark energy makes up about 68% of everything in the universe. Think about that for a moment. The stars, the planets, every galaxy, and every person, all of that normal matter accounts for less than 5% of the cosmos. The rest is this unknown, pushing the universe apart at an ever-increasing rate. Renowned physicist Brian Greene has called it the most profound mystery in all of science. So what could it possibly be? One leading idea goes back to Albert Einstein. He proposed a cosmological constant, a property of empty space itself that would exert a kind of negative pressure. But the numbers do not add up. The energy density we observe is vastly different from what theoretical physics predicts. Another possibility is that dark energy is not a constant at all, but a dynamic field that changes over time, something scientists call quintessence. We are searching for answers with powerful tools like the Hubble Space Telescope and the upcoming Nancy Grace Roman Space Telescope, which will map the cosmos in unprecedented detail. Yet the true essence of this force, this invisible hand guiding the ultimate fate of everything, remains completely unknown. It is the universe's greatest unanswered question, and its solution would force us to rewrite the laws of physics. This immense, unseen pressure shaping the cosmos finds a strange parallel on a smaller scale, within the very galaxies it pushes apart, where another type of shadowy substance exerts its own powerful grip. Galaxies themselves are hiding a secret even more tangible than the accelerating void. Watch a spiral galaxy like our own Milky Way spin. The stars on its outer edges whip around at such tremendous speeds that the entire structure should tear itself apart, flinging stars into the blackness of intergalactic space. But it does not. Something is holding it all together with an immense, unseen gravitational grip. This is the ghost in the cosmic machine, a substance we call dark matter. It is utterly invisible. It does not shine, absorb, or reflect any form of light. It only makes its presence known through its gravity, a force so strong it proves there is far more to the universe than what our eyes or telescopes can ever see. The case for this invisible cosmic scaffolding was built by the pioneering astronomer Vera Rubin. By meticulously measuring the rotation speeds of stars within galaxies, she discovered something that defied the laws of gravity as we knew them. The stars far from the galactic center were moving just as fast as those near the middle. According to Newtonian physics, without a tremendous amount of extra mass holding them in place, these outer stars should have been slowing down like planets farther from the sun. The only possible explanation was that galaxies are embedded within vast, massive halos of something we cannot see. This something, this dark matter, accounts for about 85% of all the matter in the universe. The stars, gas, and planets we consider the universe are just the glittering decoration on an immense, invisible framework. For decades, the leading candidate for this mysterious substance has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. The hunt for these ghostly particles is a story of incredible patience and engineering. Scientists have built exquisitely sensitive detectors and placed them deep underground, in old mines and beneath mountains, to shield them from the constant rain of cosmic rays that bombard the Earth's surface. Experiments with names like LUX and Xenon sit in the profound silence of these caverns, waiting for the once-in-a-lifetime tremor that might be a WIMP bumping into the nucleus of a xenon atom. So far, the silence has been deafening. No confirmed signal has ever been found. This failure has forced physicists to broaden the search, investigating other possibilities like the theoretical action, an ultra-light particle that could flow through the cosmos like a ghostly wind. Yet after all this time, with some of the most sensitive machines ever constructed, the true identity of dark matter remains a profound secret. It is the invisible hand that sculpted the universe, pulling together the first galaxies and guiding their growth, and we still do not know what it is. This hunt for the missing mass of the cosmos leads us to an even more peculiar idea, that perhaps our entire understanding of gravity itself is incomplete, a thought that echoes in the strange behavior of certain spacecraft billions of miles from home. There is a crack in the cosmological mirror, a flaw in the grand design that should not exist. When scientists mapped the faint afterglow of the Big Bang, the cosmic microwave background, they expected to see a random, featureless sea of ancient light, a final confirmation that the universe is the same in every direction. Instead, they found a whisper of order, a strange alignment that seems to connect the entire cosmos directly to us. This pattern is so unsettling that scientists gave it a dramatic name, the axis of evil. It describes how the largest fluctuations in this baby picture of the universe appear to be mysteriously lined up with the plane of our own solar system. This is a profound problem. The cosmological principle, a bedrock of modern science, states that the universe has no center and no special place. It should look roughly the same from every vantage point. The axis of evil suggests that on the grandest scale, the universe might have a preferred direction, and that direction, against all odds, seems to be pointing right at our cosmic backyard. Could this be a statistical fluke, a one-in-a-million chance that we just happen to see a pattern where none exists? Data from the incredibly precise Planck satellite has only deepened the mystery, confirming that these alignments are real and persistent. If it is not a fluke, then the implications are staggering. It could mean our understanding of the Big Bang's explosive growth, a period called inflation, is incomplete. Perhaps the universe we see is just one bubble in a vast multiverse, and the axis of evil is a bruise left from a collision with another universe in the distant past. Or maybe it points to a reality that existed before the Big Bang, a pre-existing structure that imprinted itself onto the newborn cosmos. This cosmic peculiarity forces us to confront a deeply unsettling question. After centuries of learning we are not the center of the universe, are we being told that in some strange, fundamental way, our position might be special after all? This eerie sense of a universe looking back at us finds an even more direct expression in the unnerving quiet from the stars. The same cosmos that feels strangely aligned with us also answers our calls with an unnerving silence. Billions of potentially habitable worlds are estimated to exist in our galaxy alone, a staggering number that makes the existence of other life seem almost inevitable. Yet when we train our most powerful radio telescopes on the stars, we hear nothing but a cosmic quiet. This is the heart of the Fermi Paradox, a contradiction so profound it is named for the physicist Enrico Fermi, who during a casual conversation about interstellar travel famously asked, "But where is everybody?" If life is so common, where are the signals, the probes, the grand engineering projects of other civilizations? The silence is deafening. One chilling answer is the Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the colonization of the galaxy, a barrier arises that is almost impossible to overcome. This filter could lie in our past, a rare fluke that allowed simple life to form in the first place, making us unimaginably lucky to even exist. Or, more disturbingly, it could lie in our future. Perhaps every advanced civilization eventually discovers the same technology that leads to its own inevitable self-destruction, whether through war, environmental collapse, or a runaway artificial intelligence. Our own continued survival would then not be a sign of our greatness, but merely a mark that we have not yet reached that fatal stage. Other solutions are less grim but equally strange. Maybe intelligent life evolves into forms we simply cannot recognize or communicate with, their consciousness so alien that their transmissions are indistinguishable from background cosmic noise. Perhaps they have transcended their biological forms entirely, uploading their minds into vast digital realms that require no physical expansion into space. There is even the concept of a galactic zoo, where advanced civilizations are aware of us but have agreed to observe from a distance, allowing humanity to develop naturally without interference. For over 60 years, projects like SETI, the search for extraterrestrial intelligence, have been scanning the heavens for any artificial signal, any whisper of a hello from the dark. They have sifted through countless frequencies, finding nothing but the natural hum of the universe. This great quiet forces a profound reflection. It asks us to look at our own planet, at our own technological adolescence, and consider the fragility of intelligence itself. Are we a cosmic fluke, a lonely voice in the dark, or are we simply not listening for the right thing? This contemplation of an empty channel makes the few mysterious signals we have actually picked up all the more compelling and deeply puzzling. Sometimes the universe does not whisper, it screams. For a few fleeting milliseconds, a patch of sky can unleash a blast of radio waves so powerful it outshines the entire output of our sun for 3 whole days. Then, just as suddenly, it is gone. These are fast radio bursts, or FRB, cosmic flashes first discovered in 2007, and they are some of the most intense and mysterious transient events we have ever witnessed. They arrive from galaxies billions of light years away, traveling for eons across the cosmos only to vanish in the blink of an eye. The mystery deepens with their behavior. Some of these bursts are loners, a single, spectacular shriek from the dark that is never heard again. Others are repeaters, flaring up again and again from the same patch of sky, but in unpredictable, chaotic patterns that defy any simple rhythm. This has sent astronomers scrambling for an explanation. What kind of cosmic engine can switch on and off with such violence and such speed? For a handful of these bursts, we have found a likely culprit: magnetars. These are the intensely magnetized, spinning cores of dead stars, neutron stars with magnetic fields so powerful they could strip the information from a credit card from halfway across the Milky Way. A starquake on such an object could, in theory, produce a flash that matches an FRB. Yet for the vast majority of these millisecond screams, no such source has been confirmed. The sheer power and brevity of the signals have even led to more speculative ideas, like the possibility of immensely advanced alien technology, perhaps using powerful beams to propel interstellar ships, with the flash being a side effect we happen to catch. While this is a fringe idea, it highlights just how baffling these events are. Our ability to hunt them has been supercharged by telescopes like CHIME in Canada. This unique instrument, with its stationary half-pipe design, scans the entire northern sky every day, and it has detected hundreds of these events, mapping their locations and revealing an astonishing diversity in their properties. Each new detection is another piece of the puzzle, but the full picture remains elusive. What cosmic catastrophe or exotic object can focus such unbelievable energy into such a brief, brilliant flash? The search for answers to these fleeting screams pushes us to look for other strange, transient events, the brief and violent phenomena that flash into existence and then vanish, rewriting the rules of physics in their short, spectacular lives. Amid the cosmic quiet, one signal stands out as a singular, tantalizing scream. On a quiet Ohio night in August 1977, the Big Ear radio telescope, a sprawling metal mesh listening to the sky, recorded something extraordinary. It was a narrowband radio burst, precisely the kind of signal scientists predicted an advanced civilization might use to broadcast its existence. It was so powerful, so perfect, that when astronomer Jerry Amon saw the data printout, he circled the string of letters and numbers and wrote one word in the margin: "Wow." That single word gave the signal its name and its legendary status. For 72 seconds, this blast of energy, billions of times stronger than ordinary cosmic background noise, poured in from the direction of the constellation Sagittarius. It rose to a peak and then faded away, exactly as you would expect for a signal from a fixed source in space, as the Earth's rotation carried the telescope's gaze across it. And then it was gone. For decades, astronomers have repeatedly scanned that same patch of sky, using more powerful and sensitive instruments than the Big Ear. They have listened for a repeat, for a pattern, for any hint of a follow-up. The silence has been absolute. The wow signal appeared, declared its presence with stunning clarity, and vanished without a trace. The hunt for a natural explanation has been just as frustrating. One theory suggested the signal was a reflection from a passing man-made satellite, but no known satellite matched the specific frequency and behavior. Another idea pointed to a comet, proposing that a cloud of hydrogen gas surrounding it could have emitted the signal, but the comets proposed were not in the right part of the sky at that precise time. Each potential solution has crumbled under scrutiny, leaving the wow signal in a category of its own. It remains the most compelling and most frustrating candidate for a message we may have ever received. Its brief existence is a masterclass in the challenge of SETI. It demonstrates that the universe can produce a signal that, by every definition we have, looks artificial. It fits the profile of a deliberate broadcast perfectly, and yet, without confirmation, without a second act, it remains suspended in a state of tantalizing ambiguity. Was it a cosmic mirage, a one-in-a-billion natural event we simply do not yet understand? Or was it a fleeting hello, a message that swept over our planet and was gone before we could even think of a reply? The wow signal is a ghost in the machine of science, a single, perfect data point that continues to ask us if we were ever truly alone, even for just 72 seconds. This search for a single, intelligible signal in the void leads us to consider a far more pervasive and ancient form of communication, one written not in radio waves, but in the very structure of the cosmos. There is a star in the constellation Cygnus that behaves like no other, and its strange flickers have rewritten the rules of what we thought possible. Known as Tabby star, its official designation a dry string of numbers and letters, this distant sun became an internet sensation for one simple reason. It appears to be blinking in a way that defies all natural explanation. While other stars show regular, gentle dips in brightness when a planet passes in front of them, Tabby's star does something entirely different. Its light does not dip by a predictable 1%. Instead, it plummets by up to 22% in chaotic, jagged patterns, as if something enormous and strangely shaped is drifting in front of it. The discovery was not made by a major research institution, but by a group of dedicated citizen scientists, ordinary people sifting through public data from the Kepler Space Telescope. They flagged this one star as so bizarre that professional astronomers were left utterly stumped. What could possibly block that much light from a star? The most famous and thrilling hypothesis was the idea of an alien megastructure. Imagine a civilization so advanced that it builds a vast swarm of energy-collecting panels encircling its sun, a theoretical Dyson sphere. The irregular transits could be the shadows of this colossal, incomplete construction. While this idea captured the public imagination, scientists got to work on more grounded, though still strange, natural explanations. Could it be a massive swarm of comets shattered by the star's gravity, or perhaps the aftermath of a planetary collision, a cloud of dust and debris so thick it casts these deep, uneven shadows? Follow-up observations only deepen the puzzle. Not only does the star dim in these dramatic, short-term events, but data from other telescopes showed it has also been gradually fading over years, a long-term dimming that is just as difficult to explain. The leading theory today points to very fine, uneven dust clouds, which can block light effectively without being too hot. But the exact source of this dust and the mechanism that creates such extreme and aperiodic dimming remains completely unsolved. Tabby's star has forced a new kind of astronomy, one that vigilantly monitors the sky for other stellar oddities. It taught us that the universe is capable of surprises we had not even thought to look for, and that sometimes the most profound mysteries are found not in the silence, but in a star that cannot stop winking at us. This search for shadows around distant suns leads us to a completely different kind of cosmic phantom, one that does not block light, but instead vanishes from sight entirely. Even as we search the cosmos for shadows and signals, we find that some of the most stubborn mysteries are hiding in plain sight, right here in our own solar system. For decades, two robotic pioneers were silently confounding the very laws of physics. The Pioneer 10 and Pioneer 11 spacecraft, after completing their historic missions to Jupiter and Saturn, continued their lonely journeys outward toward the stars. But as they drifted farther into the dark, something was wrong. A tiny, unaccounted-for force was acting upon them. A constant, sunward deceleration so small it was almost imperceptible. This was the Pioneer Anomaly. The deviation was minuscule, roughly 1/10 billionth of a meter per second squared. To put that into perspective, it is like measuring the slowing of a car on a highway from a distance of 100,000 miles away. Yet this tiny effect persisted year after year, a ghostly tug that accumulated over time, pulling the spacecraft slightly off their predicted courses. For years, this anomaly was a thorn in the side of physics. It suggested that our understanding of gravity, perfected by Einstein, might need revision at the vast scales of the solar system. Some theorists proposed new forms of dark matter clustered around the sun, while others explored the radical idea that gravity itself behaves differently over immense distances. The most thrilling possibility was that we were seeing the first crack in the foundation of general relativity. The solution, when it finally came, was a masterpiece of scientific detective work. It was not a new law of physics, but something far more mundane and yet brilliant. A team of researchers spent years recovering old data tapes and telemetry records, painstakingly building a computer model of the Pioneer spacecraft down to the last bolt and wire. They realized the answer was heat. The plutonium in their power generators produced a constant stream of warmth, and this thermal radiation was bouncing off the back of the spacecraft's large dish antennas. Each individual photon of heat carried a tiny, tiny amount of momentum, but over the vast surface area of the antenna and over decades of continuous emission, this created a gentle, steady push, like a soft breeze against a sail, slowing the probes down just enough to account for almost all of the anomalous deceleration. It was a thermal recoil force, a subtle effect of the spacecraft's own existence. Yet, even after this remarkable explanation, a whisper of a puzzle may remain. Some analyses suggest a tiny residual effect, a sliver of the original anomaly that the thermal model could not entirely erase. This lingering doubt keeps the door open just a crack, a reminder that our models are never truly complete. The story of the Pioneer Anomaly is a humbling lesson. It shows that the universe's secrets are not always written in grand cosmic explosions, but sometimes in the quiet, cumulative drift of a silent probe in the deep. It proves that the most profound inquiries can begin with the smallest of nudges, a principle that finds a stunning echo in the way our entire solar system moves through the galaxy. The quiet, cumulative drift of a probe is one thing, but a sudden visitor from the void is another. In October 2017, our solar system received its first confirmed tourist from interstellar space. A telescope in Hawaii spotted a faint point of light moving at blistering speeds, on a trajectory so extreme it could only have come from beyond our sun's influence. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. This was not just another asteroid or comet from our own backyard. It was a relic from another star system, and its brief flyby was packed with bizarre anomalies that continue to spark debate. The first puzzle was its shape. Based on how its brightness changed dramatically as it tumbled through space, astronomers deduced it was profoundly elongated, perhaps 10 times longer than it was wide. Imagine a cosmic cigar or a flattened pancake tumbling end over end, a form unlike any asteroid or comet we have ever seen in our solar system. The second and greater mystery was its motion. As Oumuamua slingshotted around the Sun and began its journey back into interstellar space, something unexpected happened. It sped up. It was experiencing a non-gravitational acceleration, a push that could not be explained by the Sun's gravity alone. This is a classic behavior for comets, as the Sun's heat vaporizes their icy surfaces, creating a jet of gas that acts like a natural rocket engine. But Oumuamua showed no visible coma, the fuzzy envelope of gas and dust that always surrounds an active comet. It was as dark and featureless as a piece of charcoal, so what was pushing it? The scientific community scrambled for answers. One proposal was that Oumuamua was a hydrogen iceberg, a chunk of solid molecular hydrogen that would sublimate in sunlight, giving it a push without producing any visible dust. Another suggested it was a chunk of nitrogen ice, a fragment from a Pluto-like world ripped from a distant planetary system. But each natural explanation had its own set of physical difficulties. It was this collection of oddities that led Harvard astronomer Avi Loeb to propose a more radical idea. He argued that Oumuamua's unusual shape, its high reflectivity, and its precise non-gravitational acceleration were all consistent with it being a light sail, a piece of advanced alien technology. A light sail is a thin, reflective sheet that uses the pressure of sunlight for propulsion, much like a boat's sail uses wind. Loeb suggested we might be looking at a discarded piece of such a craft, floating derelict through the galaxy. While most astronomers strongly favor a natural origin, citing the principle that extraordinary claims require extraordinary evidence, they all agree on one thing. Oumuamua's visit was far too short. We discovered it as it was already leaving, and our telescopes could only watch it fade into the distance, its secrets intact. It was a wake-up call, a celestial postcard proving that other star systems are constantly tossing material into the great dark, and we have only just begun to look. This interstellar scout challenges our categories and reminds us that the next great mystery may not be hidden in the distant cosmos, but already passing through our neighborhood, if only we are quick enough to see it. Far beyond the orbit of Neptune, in the cold, dark frontier of our solar system, a map of the frozen debris suddenly ends. Astronomers call this boundary the Kuiper Cliff, and it is one of the most abrupt and unexplained borders in our cosmic neighborhood. Imagine a vast, sprawling asteroid belt, but made of icy worlds and primordial rubble left over from the solar system's formation. This is the Kuiper Belt, and for billions of miles, its population is exactly what scientists expect. Then, at a distance of about 50 astronomical units from the Sun, the number of detectable objects plummets. It is not a gentle tapering off. It is a cliff edge, as if someone drew a line in the cosmic sand and declared nothing of significant size shall pass. This sharp cutoff defies every standard model of how a planetary system forms and settles. The gentle gravitational tugs of the known giant planets should have scattered objects much farther out, creating a diffuse population that slowly fades with distance. The Kuiper Cliff suggests something else happened, something that either cleared out that region long ago or is actively preventing objects from accumulating there today. One compelling theory points to an unseen shepherd. Could a planet, still hidden in the profound dark, be orbiting just beyond this cliff? Its gravity would act like a cosmic broom, sweeping the area clean of smaller objects, herding them inward and creating this stark boundary. This hypothetical world would not need to be a giant like Jupiter. A Mars-sized body or even a smaller Earth-like planet could have sculpted this edge over billions of years. Other explanations reach back into the solar system's violent infancy. Perhaps a passing star in the Sun's early stellar cluster swung too close and its gravity ripped away the outer material of our proto-Kuiper belt, stealing our system's most distant possessions. Or maybe the chaos of the giant planet's migration in the young solar system flung a vast swarm of objects away, leaving behind this empty zone. The New Horizons spacecraft, which gave us our first close look at Pluto, is now voyaging through this very region. As it speeds deeper into the Kuiper belt, its instruments are scanning for any faint, distant objects that might lie beyond the cliff, searching for the gravitational fingerprints of hidden worlds. The existence of this cliff is a humbling reminder that our solar system's story is not fully written. Its final chapter may still be waiting, frozen in the dark, just beyond the edge of our current sight. That empty frontier of the Kuiper Cliff is not the only strange feature in our solar system's deep freeze. Far beyond Pluto, a collection of frozen worlds is behaving as if they are being herded. These are the extreme trans-Neptunian objects, and their orbits are not randomly scattered. Instead, they are mysteriously clustered, their elliptical paths all pointing in roughly the same direction and tilting the same way against the plane of the solar system. This is a statistical anomaly so bizarre that it defies the laws of chance. It is as if you dropped a handful of marbles on the floor and they all rolled into a single, neat line. For this to happen naturally is almost impossible. Something or someone must have arranged them. In the cosmos, that someone is almost always gravity. This orbital alignment points directly to the existence of a hidden giant, a world so massive and so distant that its gravity is choreographing this distant dance from the shadows. Astronomers call this hypothetical world Planet 9. This is not a small, rocky body. Current models suggest it is a true planet, a super-Earth or a mini-Neptune with a mass 5 to 10 times that of our own world. To remain unseen, it must orbit at an almost unimaginable distance, hundreds of times farther from the Sun than Earth. At that range, a single orbit could take 10,000, even 20,000 years to complete. A single year on Planet 9 would span the entirety of recorded human history. The search for this ghost planet is a monumental challenge. Its incredible distance means it reflects virtually no sunlight, making it 1 billion times fainter than what we can see with the naked eye. Astronomers are using some of the world's most powerful telescopes, like Subaru in Hawaii and the Pan-STARRS survey, to scan vast swaths of the sky, looking for one faint, slow-moving dot among countless stars. They are searching for the predicted gravitational signature, not the planet itself. They calculate where Planet 9's gravity should be, based on the orbits of the objects it seems to be shepherding, and then they point their telescopes at that specific patch of dark sky, hoping to catch a glimpse of the shepherd itself. If it is real, what is it? One captivating theory is that Planet 9 is not native to our solar system. It could be an exiled world, an orphaned exoplanet that was captured by our Sun's gravity as it drifted through the galaxy in its infancy. Alternatively, it might be a primordial remnant, a core of a giant planet that formed in the outer reaches and was never consumed by Jupiter or Saturn. Its discovery would be more than just adding a new world to our charts. It would be a window into the solar system's most violent and formative era, rewriting the story of our own cosmic backyard. The enduring mystery of Planet 9 proves that even the spaces we think we know can hide colossal secrets, and that the gravitational tug of the unseen can be the most compelling clue of all. At the heart of our own galaxy, a silent, invisible fire burns. The center of the Milky Way should be a place of predictable chaos, governed by the known physics of stars and our supermassive black hole, Sagittarius, a star. Yet when the Fermi Gamma Ray Space Telescope mapped this region, it found a persistent and brilliant glow of gamma ray light, the most energetic form of radiation in the universe. This is the galactic center excess, a shining fog of high-energy photons that simply should not be there according to our best models. It is as if the core of our home galaxy is hiding a secret engine, one that runs on a fuel we cannot see. The most tantalizing explanation points directly to the universe's greatest ghost, dark matter. Billions of these hypothetical particles could be swarming in the dense galactic core, and if they are their own antimatter counterparts, they would annihilate upon contact, converting their mass directly into a flash of gamma rays. This glow could be the first indirect evidence of dark matter's true nature, a ghostly substance finally revealing itself through self-destruction, but the cosmos is rarely so straightforward. Other suspects are in the frame. The excess could be produced by a vast, unseen population of millisecond pulsars, the rapidly spinning corpses of dead stars. These cosmic lighthouses beam out intense radiation, and if enough of them were clustered in the galactic center, their combined output could mimic this diffuse glow. Another possibility reaches back in time to the violent tantrums of Sagittarius, a star itself. Perhaps in the distant past, our central black hole experienced a colossal outburst, a feeding frenzy that accelerated particles to near light speed, and the remnant of that ancient cataclysm is the energy we see today. The key to solving this mystery lies in the pattern of the light itself. If the glow is perfectly smooth and spread evenly, it favors the dark matter explanation. But if powerful new telescopes can resolve it into pinpricks of light, individual pulsars would be the likely culprits. So far, the maps remain frustratingly ambiguous, a smooth haze with just a hint of a lumpy texture that keeps both possibilities alive. This energetic puzzle at the very core of the Milky Way forces us to look deeper, to question whether we are seeing the death throes of the universe's most elusive substance, or merely the combined breath of countless stellar ghosts. It is a reminder that sometimes the brightest secrets are hidden in the most brilliant lights. Even as dark matter's immense halo seems to hold galaxies together, its smaller counterparts are causing a major headache for cosmologists. Picture a grandparent galaxy with two smaller satellite galaxies orbiting around it, seemingly connected by a faint, luminous bridge of stars. According to our most trusted models, these satellite galaxies should each be embedded within their own massive, puffy halo of dark matter, moving in a slow, stately dance dictated by that invisible gravity. But their observed motions are far too fast and far too coordinated. It is as if they are not independent islands at all, but are somehow tethered together, moving in a synchronized flow that defies the expectation of their dark matter anchors. This is the essence of the tethered galaxy problem. It creates a direct challenge known as the too big to fail problem, where the satellites we see are simply too bright and massive to exist within the small, weak dark matter halos that simulations predict for them. Their very existence should be impossible. The plot thickens when we look at our own cosmic backyard. Both the Milky Way and the Andromeda Galaxy have their satellites arranged not in a random, spherical swarm, but in vast, thin, rotating planes like flies caught on a single, invisible disk. This is the planes of satellites issue. For this to happen by chance in a universe dominated by dark matter halos is astronomically unlikely. It is like throwing a handful of confetti into the air and watching it land in a perfect, flat circle. These are not minor quirks. They are fundamental structural puzzles that test the very core of our cosmological model, known as lambda CDM. If dark matter behaves exactly as we think, these satellite systems should not look like this. So what is the solution? Some physicists are exploring a fascinating alternative called self-interacting dark matter. In this model, dark matter particles do not just pass through each other like perfect ghosts. They can occasionally collide and scatter, smoothing out the inner regions of halos and potentially allowing for the kind of structures we observe. Others look to the complex, messy physics of ordinary matter, the baryonic physics of supernova explosions and galactic winds, which could have reshaped these small galaxies in ways our simulations are only beginning to capture. And then there is the radical possibility that we have gravity itself all wrong, that a theory of modified gravity could explain these motions without any dark matter at all. Each of these galactic-scale anomalies forces a profound re-examination of how galaxies assemble and evolve. They remind us that the map is not the territory, and that our most beautiful simulations are still approximations of a far more complex and wondrous reality. These structural flaws in our local universe are just a prelude to the truly colossal mysteries that emerge when we zoom out to the largest scales of all. Our galaxy is not sailing freely through the cosmos. It is caught in a relentless river pulled by a force we cannot see. This is the Great Attractor, a gravitational anomaly of staggering proportions located in the direction of the constellations Centaurus and Norma. Everything in our local galactic neighborhood, including the Milky Way, is flowing toward this single point in intergalactic space at a breathtaking speed of over 600 kilometers per second. The source of this immense pull is hidden from our direct view, lying directly behind the thick, dusty plain of our own galaxy, a region astronomers call the zone of avoidance. It is as if the key to understanding our motion is locked in a cosmic vault, obscured by the very stars and dust of our home, but we have learned to see with new eyes. By peering through the dust with infrared and X-ray telescopes which can penetrate the visual clutter, astronomers have begun to map this forbidden zone. They have found the Norma cluster, a dense gathering of galaxies, sitting at the heart of the Great Attractor. Yet even this massive cluster does not seem to have enough gravity to account for our entire motion. The true source appears to lie even further away, in the direction of the Shapley supercluster, an almost unimaginable concentration of mass and galaxies. So what is really pulling us? Is the Great Attractor a single, supermassive supercluster we have yet to fully map? Or is it the sign of something even more profound, a knot in the cosmic web where dark matter has pooled into an overwhelming concentration? This gravitational tug-of-war reveals that the empty spaces between galaxies are not empty at all. They are structured by invisible filaments of dark matter, a cosmic geography that guides the flow of entire galaxies like water flowing downhill. Our journey toward this unseen attractor forces us to confront the ultimate fate of not just our galaxy, but of entire clusters, all moving in a silent, coordinated dance dictated by the hidden architecture of the universe. This fundamental parameter, the rate of the universe's expansion, is now the subject of a deep and growing crisis. We call it the Hubble constant, a number that tells us how fast the cosmos is stretching at any given moment. It should be a single, universal value, a fixed feature of reality, but it is not. We are getting two different, stubbornly conflicting answers, and the gap between them is widening into a chasm. One answer comes from looking at the ancient universe by studying the faint afterglow of the Big Bang, the cosmic microwave background. This pristine snapshot allows us to calculate what the expansion rate should be today, based on the standard model of cosmology. The other answer comes from measuring the modern universe by watching how the light from nearby stars, Cepheid variables and supernova, tells us their distance and speed. These two methods, the ancient and the local, should meet perfectly. They do not. The local measurements consistently give a faster, more frantic expansion rate than the predictions from the early universe. This is the Hubble tension. It is as if you calculated how fast a car should be moving based on its acceleration from a stoplight. But when you actually clock it with a radar gun miles down the road, it is going significantly faster. The difference is not a small rounding error. It is a persistent, statistically significant discrepancy that has survived years of increasingly precise observations. So what is happening? The most conservative explanation is that there is a hidden flaw, an unknown systematic error in one of our measurement techniques. Perhaps our understanding of Cepheid variable stars, the cosmic yardsticks we rely on, is subtly incomplete. Or maybe there is some dust or other effect in local galaxies that we have not accounted for, tricking our instruments. This is the focus of immense efforts like the SH0ES collaboration, which is painstakingly refining the distance ladder, and the James Webb Space Telescope, whose sharp infrared vision is now peering at these same stars to check and recheck the work of its predecessor, Hubble. But if the discrepancy holds, if it is proven to be real, then the implications are staggering. It would mean our standard model of cosmology, the lambda CDM model that has been so successful, is missing a crucial ingredient. The universe's expansion is not following the script we wrote for it. This could point to dark energy being more complex than a simple constant. Maybe it is evolving, growing stronger over time. Or perhaps there are extra, unknown types of subatomic particles like sterile neutrinos flooding the cosmos and subtly altering its expansion history. Resolving this tension is not an academic exercise. The Hubble constant is directly tied to the age of the universe and its ultimate fate. A faster expansion rate means a younger cosmos and a more rapid, lonely end. This single number connects to everything from the largest scales of dark energy to the smallest particles. making its current disagreement one of the most pressing and fundamental puzzles in all of modern science. Our very origin story is missing a key ingredient. In the first frantic minutes after the Big Bang, the universe was a seething nuclear furnace, forging the lightest elements in a process called Big Bang nucleosynthesis. Our most sophisticated models of this primordial cooking predict exactly how much hydrogen, helium, and a specific isotope called Lithium-7 should have been created. For hydrogen and helium, the predictions match the amounts we observe in the oldest stars almost perfectly, but for lithium, the numbers are catastrophically wrong. The ancient, pristine stars in the halo of our galaxy, which act as cosmic time capsules preserving the chemistry of the early universe, show only about 1/3 of the Lithium-7 that our theories insist must be there. This is the cosmological lithium problem. For decades, scientists have searched for the source of this discrepancy. Could our understanding of the nuclear reaction rates inside those first few minutes be subtly incorrect? Perhaps the lithium is being destroyed inside these ancient stars themselves, sunk from their atmospheres into hotter interior layers by some poorly understood mixing process. But even after refining these stellar physics models to an incredible degree, the lithium deficit stubbornly remains. This forces physicists to consider far more radical solutions. One idea involves the hypothetical action, the same particle proposed as a candidate for dark matter. In the intense heat of the infant cosmos, actions could have been produced in abundance, and their decay might have altered the nuclear reactions just enough to suppress the creation of Lithium-7. Another possibility challenges the Big Bang scenario itself, suggesting conditions in the first moments were different, perhaps with a varying neutron-to-proton ratio that would have changed the entire nuclear chain reaction. The missing lithium is more than a small accounting error. It is a fundamental crack in our model of the universe's first moments, a direct link between the behavior of elusive subatomic particles and the chemical makeup of the cosmos we see today. Solving it would not just tell us where the lithium went, it would reveal new physics that govern the birth of everything. The universe is constantly pelting our planet with bullets of pure energy. These are ultra-high energy cosmic rays, subatomic particles that arrive from deep space carrying energies far beyond anything we can produce in our most powerful particle accelerators. Some of these particles possess a kinetic energy equivalent to a well-thrown baseball, all compressed into a single, microscopic proton or atomic nucleus. They are the fastest, most energetic individual particles known to exist, and according to our best theories, they should not be able to reach us at all. This is the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. At these unimaginable energies, a particle traveling across the vast intergalactic distances should constantly bump into the photons of the cosmic microwave background, the leftover glow from the Big Bang. Each collision would steal a little of its energy, slowing it down over millions of light years until its energy falls below this theoretical limit. The fact that we detect these particles at all means they cannot have come from very far away. They must be relatively local, originating within our own galactic neighborhood or from nearby galaxies. Yet when scientists at observatories like the immense Pierre Auger Observatory in Argentina try to trace these particles back to their source, they hit a wall of confusion. The paths of these charged particles are not straight lines. They are bent and twisted by the weak but pervasive magnetic fields that fill the space between galaxies. It is like trying to trace a single raindrop back to its cloud in the middle of a hurricane. The rain is falling everywhere, but the wind has scrambled its direction completely. The most powerful cosmic ray ever detected was so energetic it was nicknamed the "Oh my God" particle. When it struck the atmosphere in 1991, It carried the energy of a brick dropped from waist height, all in a single subatomic speck. Its arrival direction pointed vaguely out into empty space, with no obvious violent event to explain its origin. The search has narrowed to the most extreme objects we know. Could supermassive black holes at the hearts of active galaxies be firing these particles like a cosmic railgun? Are they the aftermath of colliding galaxies or the violent deaths of hypergiant stars in gamma-ray bursts? The Auger Observatory has mapped thousands of these events and found a faint, tantalizing correlation with the positions of nearby galaxies with active cores. But it is not a perfect match. For every handful of particles that seem to point toward a known cataclysm, another arrives from a void of cosmic quiet. The true accelerators remain hidden, their identities shielded by magnetic fog. The very existence of these particles tells us that somewhere, not too far away in cosmic terms, engines of unimaginable power are at work. They are processes that can focus more energy into a single proton than the Sun will emit in its entire lifetime. We are being bombarded by the shrapnel from explosions we cannot see, fired from guns we have yet to find. This search for the universe's most powerful particle accelerators leads us to a different kind of extreme, to places where the fabric of reality itself is stretched to its absolute limit. The ultimate prison might not be a place of confinement, but a gateway to oblivion. According to Einstein's general relativity, a black hole is defined by its event horizon, a point of no return where the gravitational pull becomes so intense that not even light can escape. Anything that crosses this boundary, from a single atom to an entire library of information, is thought to be lost forever to the outside universe, crushed into the infinitely dense singularity at the center. This presents no problem for classical physics, but when we introduce the bizarre rules of quantum mechanics, a fundamental law of the universe is violated. Quantum theory states that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. If you were to burn a book, the information contained in its letters is not gone. It is merely converted into the specific arrangement of smoke particles and ash. A being with infinite knowledge could reverse the process and reconstruct the book. A black hole, however, seems to be the ultimate shredder. It allegedly takes the information of whatever falls in and obliterates it completely. This is the black hole information paradox, a direct conflict between our two most successful theories of reality. The crisis deepens with Stephen Hawking's revolutionary discovery. Hawking realized that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak a faint glow of radiation. This Hawking radiation is thermal, meaning it is random and featureless, carrying no information about what fell inside. Over trillions of years, this process causes the black hole to evaporate, eventually vanishing entirely. So what happens to the information of the star that collapsed to form it, and all the planets and particles it ever consumed? If it is lost with the black hole's demise, then the universe is fundamentally unpredictable, and a core pillar of physics is wrong. Physicists have proposed stunning solutions to rescue the information. One of the most profound is the holographic principle. This idea suggests that all the information about everything within a black hole's three-dimensional volume is not lost inside, but is instead perfectly encoded on its two-dimensional surface, the event horizon. It is like a cosmic DVD where a three-dimensional movie is stored on a two-dimensional disc. The information is never actually destroyed, just stored in a way we do not yet fully understand. Another possibility is that evaporation stops at the very last moment, leaving behind a tiny, information-packed remnant, a fossil of the black hole's entire history. Recent breakthroughs are giving us new ways to investigate this puzzle. The study of gravitational waves from colliding black holes provides a real-world laboratory. Some theories predict that the event horizon is not perfectly smooth, but has quantum structure, and that mergers might produce faint echoes in the gravitational wave signal, a whisper of the information preserved on the surface. The concept of black hole soft hair suggests that even empty space around the horizon can imprint itself with infinitesimal records of what has passed through. Solving the information paradox is not just an academic exercise. It strikes at the heart of whether the universe is deterministic, if the past uniquely defines the future, and what truly happens to reality when it encounters the most extreme gravity imaginable. The answer will force us to rewrite our understanding of space, time, and information itself, revealing if black holes are the ultimate vaults or the ultimate voids. We have inventoried the stars, the galaxies, and the cold gas, and we are still coming up short. The universe seems to be missing half of its ordinary matter. This is the missing Baryon problem, a cosmic accounting error of epic proportions. Baryons are the particles that make up everything we can see and touch, from the planets to our own bodies. The Big Bang's primordial recipe tells us exactly how much of this normal matter should exist. When we add up all the visible material in stars, galaxies, and the cool gas clouds we can easily see, we only account for roughly half of what the models insist must be there. So where did the rest of the universe's building blocks go? The leading suspect is a ghostly, superheated fog known as the warm-hot intergalactic medium, or the WIM. This is not a solid, liquid, or gas as we know it. It is a tenuous plasma, a soup of protons and electrons so incredibly diffuse that a single cubic meter of it might contain only a single particle. Yet, because it fills the vast voids between galaxies and weaves through the cosmic web, its total mass is staggering. It is the ultimate needle in a haystack, a phantom that reveals itself only in the most indirect ways. When the brilliant light of a distant quasar travels for billions of years to reach us, it passes through these filaments of invisible hot gas. Specific wavelengths of that light are absorbed, leaving faint, telltale dips in the quasar's spectrum. It is like seeing the shadow of a whisper. X-ray telescopes like XMM Newton hunt for the WIM by looking for the faint glow this million-degree gas emits. Slowly, painstakingly, these observations are confirming that the missing baryons were hiding in plain sight all along, woven into the grand architecture of the cosmic web. This successful hunt for ordinary matter is a profound relief for cosmologists, as it closes a major gap in our understanding of the universe's contents. But it also sharpens a far more unsettling reality. We have now accounted for 100% of the ordinary matter, yet this normal stuff, the atoms of our reality, make up less than 5% of the cosmos. The rest is the dark, unknown realm of dark matter and dark energy, a shadow universe whose true nature remains the ultimate prize. The smallest galaxies are telling us that dark matter might be softer than we thought. The ghostly halos that hold galaxies together should be at their most dense right at the center, forming a sharp peak or cusp of invisible matter. Yet when astronomers measure the rotation of stars within tiny dwarf galaxies, they find something deeply puzzling. The stars are moving too slowly in the inner regions. The dark matter there is not forming a steep cusp. Instead, it appears to have been smoothed out into a gentle core. This is the Core-Cusp Problem, a small-scale rebellion against our grandest cosmic models. It is as if the ghost has a gentler touch than our equations predicted. How could this happen? One compelling idea is that dark matter is not completely ghostly after all. Perhaps dark matter particles can interact with each other, not through electromagnetism, of course, but through some unknown force. When these particles collide and scatter, they would effectively smooth themselves out, redistributing the dense central peak into a flatter, more uniform core. Another possibility brings the ordinary universe back into play. The violent lives and deaths of stars, the tremendous energy from supernova explosions, can blast through a dwarf galaxy. This baryonic feedback acts like a cosmic mixer, churning the galaxy's center and physically pushing the dark matter around, carving out a core from what was once a cusp. Then there is the radical alternative, a theory known as modified Newtonian dynamics, or MUND. This idea proposes that we do not need dark matter at all, that gravity simply behaves differently at very low accelerations, like those found in the faint outskirts of galaxies. For these dwarf systems, MUND can sometimes reproduce their rotation curves quite well, but the theory faces its own monumental challenges, particularly when explaining the behavior of entire galaxy clusters, where the observed gravitational effects are far too strong for MUND to explain without invoking some form of hidden matter anyway. The true answer likely lies in a more complex dance between the dark and the light. Cosmologists are now running immensely detailed supercomputer simulations that model not just the dark matter scaffolding, but also the gassy, chaotic, star-forming baryonic world. The goal is to see if this realistic feedback can indeed sculpt the dark matter cores we observe. This tiny anomaly in the smallest galaxies is forcing a big revision. It is probing the fundamental properties of the universe's most abundant matter, asking if it is truly an inert ghost or something with a subtle, complex life of its own. The solution will not just tell us what dark matter is, but how it dances with the universe we can see. Stretching across an almost unimaginable billion light years, a profound emptiness lurks in the constellation Eridanus. This is the Eridanus Supervoid, a cosmic desert so vast and barren that it defies easy explanation. Its presence is felt not by what it contains, but by a shadow it casts upon the oldest light in the universe. When scientists created the most detailed map of the cosmic microwave background, they found a large, anomalously cold spot that seemed to align with this void. It is as if the universe has a chill, a place where the afterglow of creation is just a little bit fainter. The leading theory to explain this involves a subtle, mind-bending gravitational effect. As light from the cosmic microwave background travels through the cosmos, it passes in and out of the gravitational wells of galaxies and clusters. Normally, the energy it gains falling in is lost climbing out. But in an expanding universe dominated by dark energy, these gravitational wells are slowly weakening over time. A photon passing through a vast, growing void like the Eridanus Supervoid would actually lose a tiny bit of net energy climbing out of a potential that is becoming shallower as it travels. This is the integrated Sachs-Wolf effect, and it would make the light appear ever so slightly colder, imprinting a cold spot on the CMB map. The problem is one of scale. The observed cold spot is so significant, and the proposed supervoid, while enormous, may not be quite empty enough to produce the effect we see. The numbers do not perfectly add up, leaving a gap in our understanding. This mismatch has led to more exotic proposals. Could this be evidence of a collision with another universe in a vast multiverse, a cosmic bruise left from an impact in the primordial cosmos? Or does it point to physics we have not yet discovered, a strange property of dark energy or spacetime itself? Surveys like the Dark Energy Survey have meticulously mapped the large-scale structure in this direction, confirming the existence of a significant underdense region, but continuing to debate its precise connection to the CMB feature. The Eridanus Supervoid is more than just an empty space. It is a profound challenge to our models of how structure forms in the universe, forcing us to question if such immense emptiness is even statistically possible within our standard cosmological story. This cosmic chill asks us if we are seeing a simple shadow or the silhouette of something from beyond our own reality. The frozen fringes of our solar system are haunted by celestial recluses, worlds that follow paths so strange they seem to defy the sun's command. Among them is Sedna, a reddish dwarf planet on a lonely 10,000-year orbit that never brings it anywhere near the giant planets. Its elongated path swings from a distant point 76 astronomical units from the Sun out to a staggering 937, a trajectory so extreme it exists in a detached, solitary realm. Sedna is not alone. Other objects like it, such as the provocatively nicknamed 2012 VP-113, share this peculiar characteristic, their orbits tilted and stretched, their closest approaches to the Sun too far out to be influenced by Neptune's gravity. They are cosmic hermits, forever isolated from the planetary dance that defines the inner solar system. Their very existence is a celestial crime scene, and the evidence points to a violent disruption in our system's past. How did they get there? One compelling theory is that a passing star in the Sun's early stellar nursery swung close enough billions of years ago to gravitationally fling these objects into their current exiled orbits. Another suggests the giant planets themselves migrated outward in a chaotic ballet, their shifting gravity scattering primordial bodies like Sedna into the deep freeze. But the most tantalizing clue is the pattern they create. The orbits of these extreme objects are not just random. They cluster, their points of closest approach aligned in a way that strongly hints at the persistent gravitational shepherd we call Planet 9. Each new discovery of these distant fossils adds another data point, another whisper from the past telling a story of a solar system far more dynamic and violent than the serene model we often picture. They are the ancient scars of a formative era, and by reading their paths, we are slowly piecing together the true, tumultuous biography of our own cosmic home. Etched across the radio sky are ghostly structures of immense scale. These are the galactic radio loops, colossal arcs of energy that can span a third of the visible heavens, yet remain invisible to our eyes. They glow only in the long, silent wavelengths of radio light, revealing a hidden anatomy of our galaxy. The most famous of these, the North Polar Spur, rises from the galactic center like a vast celestial wave, while Loop I forms another enormous ring, a bubble of energy so large it could envelop entire star clusters. For decades, their true nature has been a subject of quiet debate. The leading theory suggests they are the faded scars of ancient supernova, the expanding shock waves from stellar explosions that occurred millions of years ago. These blasts would have carved out bubbles in the interstellar medium, their remnants still glowing with synchrotron radiation as electrons spiral along the faint magnetic fields of the galaxy. But the puzzle is not so easily solved. Pinpointing their exact distance has been notoriously difficult. Are these loops relatively nearby, perhaps connected to the local bubble, a region of hot, thin gas that our own solar system is drifting through, a cavity itself thought to be carved by multiple supernovae? Or are they much more distant, immense structures woven into the very magnetic fabric of the Milky Way's spiral arms? The answer changes everything about their power and origin. New eyes on the cosmos are finally bringing these faint giants into focus. Radio telescopes like LOFAR, with its vast network of antennas, are mapping the sky with stunning sensitivity, revealing finer details in these loops than ever before. The upcoming square-kilometer array promises to be even more revolutionary, a telescope so powerful it could listen to a mobile phone on Mars, and it will scan these radio ghosts to determine their precise age and the mechanics of their birth. These silent arcs are a lasting echo of the violence that shapes galactic ecosystems. They are the faint, lingering breath of dead stars, a reminder that the calm night sky is a palimpsest with the stories of ancient cataclysms written just beneath the surface, waiting for the right kind of light to be read. Even the rain of cosmic rays from deep space falls with a hidden pattern. While we struggle to trace individual particles back to their source, a broader, more subtle signal emerges when we look at the sky as a whole. Across the entire celestial sphere, the arrival rate of these high-energy particles is not perfectly uniform. There is a slight but persistent imbalance, a gentle slope in the data where one hemisphere of the sky seems to receive just a few % more cosmic rays than the opposite hemisphere. This is the Lomonosov-Ryle effect, a large-scale anisotropy that reveals a fundamental lopsidedness in our local cosmos. It is as if we are sailing through a cosmic weather system, with a faint but constant wind of particles blowing from a particular direction. The leading explanation points to our own motion through the galaxy. As our solar system orbits the Milky Way, it might be plowing through a relatively calm sea of galactic magnetic fields and plasma, creating a kind of headwind effect. The particles arriving from the direction we are heading towards would appear slightly more energetic and numerous, while those catching up from behind would be statistically fewer, creating this observed dipole. But the data from vast observatories like the Pierre Auger Array adds deeper layers to the puzzle. The exact alignment and strength of this dipole do not perfectly match the simple model of our galactic motion alone. This suggests that the sources of these cosmic rays are not evenly distributed around us. We might be living in a celestial neighborhood that is curiously lopsided, with a greater concentration of powerful cosmic accelerators, like recent supernova remnants or active galactic nuclei, located in one particular direction of the sky. Alternatively, the magnetic fields that guide these charged particles on their billion-year journeys might be far more complex and structured than we thought. Vast, invisible magnetic lenses in the interstellar medium could be focusing this particle rain, creating bright and dark patches in the cosmic ray sky. Pinpointing the cause of this subtle asymmetry is like trying to map the ocean's currents by watching the pattern of driftwood washing ashore. Each piece has been tossed and turned by countless waves and hidden eddies. By studying this dipole, scientists are not just looking for where the particles come from, but also charting the invisible magnetic geography of our galactic arm. It is a reminder that even in the most chaotic and energetic phenomena, the universe leaves behind a faint, ordered signature, a whisper of the large-scale forces that shape everything. A perfect geometric shape hangs in the cosmic dark, a structure so precise it seems crafted by an unseen hand. This is the Red Rectangle Nebula, a bipolar nebula surrounding the binary star system HD 44179, and it stands apart from every other cloud of gas and dust in the heavens. While most nebulae are ethereal and irregular, billowing like smoke, this one presents a stark, almost architectural form. Its defining feature is a near-perfect rectangular outline, a shape so unnatural for space that its very existence demands an explanation. But the geometry deepens. Within that red frame lies an even more intricate secret, a series of complex, ladder-like rungs made of dust, ascending symmetrically from the central star. It is a cosmic xylophone, a staircase to nowhere, etched in the void. The leading theory points to the central binary stars as the architects. As these two stars orbit one another, they eject gas and dust in a dense disk, and outflows from the poles of this system are sculpted by stellar winds into that iconic conical shape. From our vantage point, looking directly at the narrow end of the cone, It appears as a perfect rectangle. The stunning rungs are thought to be the result of periodic mass loss, like puffs of smoke from a smokestack, ejected at regular intervals during the star's complex dance. The rich red color comes from a specific type of light emission, likely from large hydrocarbon molecules known as polycyclic aromatic hydrocarbons, effectively a cloud of complex organic soot illuminated by the starlight. Yet for all this understanding, profound puzzles remain. The exact mechanism that carves the rungs with such precision is not fully understood. What clockwork in the binary system dictates the timing and density of these puffs? Hubble Space Telescope images have revealed the structure in breathtaking detail, but they have also deepened the mystery, showing a level of symmetry and order that our models of stellar death struggles to replicate. The Red Rectangle is a beautiful contradiction. It is a phenomenon born from chaotic stellar winds and gravitational tides, yet it results in one of the most orderly structures we have ever witnessed. It challenges our assumptions about the final acts of sun-like stars, proving that even in death, a star can create a legacy of baffling geometric art. This celestial artwork, forged in the death throes of a star, finds a strange parallel in the violent birth of another, where a single, impossibly bright flash rewrote the rules of stellar cataclysms. The universe is not just expanding, it is tearing itself apart from the inside. In the vast cosmic web of galaxies, filaments, and clusters, there exists a whole of staggering proportions. In the constellation of Boötes, the herdsman, lies a sphere of near-nothingness so vast it could swallow thousands of galaxies whole. This is the Boötes Void, a cosmic cavern measuring 330 million light-years across. Its sheer scale defies simple explanation, a gaping wound in the fabric of the cosmos that contradicts our expectation of a roughly uniform universe. Standard cosmological models predict matter should be distributed more evenly, not gathered into such an immense, empty pocket. How could a region this large end up with almost nothing in it? The void is not completely barren. A handful of galaxies, perhaps 60 in total, have been found drifting in this unimaginable emptiness like lonely ships on an endless, dark ocean. Their very isolation is a clue. Studies of their motion reveal they are not static. The void itself is growing, its gravitational influence pulling these few galaxies outward, away from its center in a slow, inexorable flow. This makes the Boötes Void a unique natural laboratory. Here, in the absence of overwhelming local gravity, we can see the pure, unadulterated effects of dark energy at work, the force that pushes the universe apart acting on a grand, empty stage. The profound silence of this place is more than an absence of light. It is a physical manifestation of the questions we still cannot answer. How did such a colossal void form in the first place? Was it the result of a merger of many smaller voids over billions of years, or does its existence point to a more exotic origin in the earliest moments of the Big Bang? The Boötes Void stands as a monument to the unknown, a chilling reminder that the greatest mysteries are not always found in the brilliant lights of the cosmos, but in the deep, resonant silence between them. Yet the relentless expansion and silent voids lead us to a mystery so fundamental we experience it with every heartbeat. Time itself is the 27th unsolved enigma, a river that flows in only one direction. Why does the past feel different from the future, and why can we only move forward into the unknown? This is the arrow of time, a cosmic and philosophical puzzle that ties the largest scales of the universe to our most intimate moments of memory and anticipation. The most compelling clue comes from the concept of entropy, a measure of disorder in a system. The universe as a whole is constantly moving from a state of low entropy to high entropy, from order to disorder. Think of a hot cup of coffee left on a table. It will always cool down to room temperature, its heat dissipating into the air. You will never see the surrounding air spontaneously concentrate its energy to reheat the coffee. This one-way process is a local example of the cosmic rule. The ultimate low-entropy state was the Big Bang itself, an unimaginably ordered and compact beginning. The entire subsequent history of the universe, from the formation of galaxies to the burning of stars, is just the long, slow unraveling of that initial order, the cosmic coffee cooling for 13.8 billion years. But this raises a profound question. Why was the Big Bang in such a low entropy state to begin with? What set that initial condition that gave time its arrow? Some physicists like Sean Carroll suggest the answer lies in the multiverse. In an eternal, larger reality, our Big Bang was just a fluctuation, a rare low-entropy bubble in an infinite sea of high-entropy chaos. In this view, our arrow of time is not universal. It is a local property of our particular cosmic patch, and other universes might have arrows pointing in different directions, or even no arrow at all. The nature of time becomes even stranger when we consider extreme gravity. According to Einstein, time is not a universal constant. It is a dimension woven into the fabric of space-time, and it can be stretched and warped. Near a black hole, gravity is so intense that time slows to a crawl relative to a distant observer. An astronaut falling toward the event horizon would appear from the outside to freeze in time, their final moments stretched across eternity. For the astronaut, however, time would pass normally until they met their fate. This relativity of time forces us to ask if our conscious experience of a flowing present is just a biological illusion, a useful trick evolution gave us to navigate a world of increasing disorder. Is the past, present, and future all equally real, laid out in a static four-dimensional block universe, with our minds simply tracing a path through it? The mystery of time transcends astronomy and physics, touching the core of our own existence. It asks us what it means to be a conscious creature in a universe that started in a state of exquisite order and is now rushing toward a cold, dark, and disordered end. We are not just observers of this cosmic story. We are living expressions of time's one-way flow, our very consciousness a product of the universe's journey from a singular beginning toward an uncertain future. This journey through 26 cosmic enigmas reveals a universe that is profoundly and beautifully unfinished. Each of these mysteries, from the silent push of dark energy to the gravitational grip of dark matter, from the wow signal's singular cry to the herded orbits of distant worlds, represents a frontier of our ignorance. They are not failures of science, but its very fuel. Every time we solve one puzzle, it peels back a layer to reveal deeper, more complex questions beneath, a cascade of wonder that ensures the cosmos will never grow dull. These are the open invitations, the cosmic challenges that drive humanity to build more powerful telescopes, to launch daring space missions, and to dream of theoretical breakthroughs that will rewrite our textbooks. The next great discovery is waiting, not in a dusty archive, but in the silent data stream of a new radio telescope or in the faint, anomalous flicker of a star 1,000 light-years away. So the next time you find yourself under a clear night sky, let your gaze wander. Remember that you are not just looking at points of light, but at a living, breathing puzzle box filled with invisible forces, ghostly matter, and whispers from the void. Let these unsolved questions fill you with a sense of boundless potential. Which of these 26 mysteries captivated your imagination the most and made you question everything you thought you knew? Share your thoughts in the comments below and subscribe to continue exploring the universe's greatest secrets together.